Okay, 27 is kind of a subtle question. It says, so which of the following would require the greatest volume of base in order to reach a pH of 7? So if we're starting with an acidic solution, we need to add base. Okay, we can eliminate answer D. Okay, answer D here, this is going to be a neutral solution already, so it's already at a pH of 7, so we would have to add 0 base to that, so that's not the greatest volume of base. Okay, we have C, that is a strong acid, okay, and A, that's the same concentration of a weak acid. So we might think, well, they're going to take the same amount of base, but they would take the same amount of base to neutralize, but when HNO2 is neutralized, it is not going to be a pH of 7, because since it's a weak acid, it's going to start forming the conjugate base of that weak acid to make it slightly more basic. So it's going to turn out it's going to take a little bit less to take that guy to pH of 7 than it would HNO3. So it's actually going to be this one here, the HNO3. And B is even worse because we're already putting in some of the conjugate base. Okay, so that's going to even have a less distance to go. So the answer C, that strong acid, is going to take the most NaOH in order to reach a pH of 7. Number 28, okay, what volume of KOH was needed to titrate 40 milliliters of 0.75 molar HClO2 to its half equivalence point. So let's just make a little trick on here and say, well, instead of saying 40 milliliters, let's just say how much would it take to completely neutralize 20 milliliters. And because this has one OH and this has one H, we can do our shortcut and use our dilution formula that the volume times the molarity of our acid is equal to the volume times the molarity of our base. Okay, so we could say that we have 20 milliliters of 0.75 molar acid. Okay, is going to equal what milliliters of 0.15 molar, okay, of our base. And we can see that our acid is 5 times more concentrated. That means we're going to need 5 times more of our base. So instead of 20 milliliters, we're going to need 100 milliliters. So the answer is B. Okay, alternatively, we can go back and do a stoichiometry problem. Okay, starting with, volume. Again, we're only going halfway, so I wouldn't use 40, I'd use 20 milliliters. And if I had 20 milliliters, I'd go milliliters to liters. Okay, I'd go liters to moles using the 0.75. Then I'd have my balanced equation where 1-to-1 mole ratio. And then I would go from moles to liters using molarity, and I would end up with the same answer. Number 29. If I have HNO2 solution and NaOH is added until the pH of the mixture is 5, how do the concentrations of the species compare? Okay, the pKa of HNO2 is 3.40. Well, that's an important clue right there. And what that tells us is that if the pH were 3.40, then we know in our buffer the HNO2 concentration would be equal to the NO2 minus concentration. So those two would be equal if the pH were 3.40. But we're doing a situation where the pH is 5.0. Okay, so that means we must have a little bit more basic, must have a little bit more of the base. So the NO2 is greater than the HNO2. So let's check our answers now with just knowing that much. So we know NO2 is greater than HNO2. And so that is true for A, the NO2 is greater than HNO2. And in B, they're saying they're equal. That would only be true at pH of 3.4. And here, C, the HNO2 is greater than the H plus, which is equal, no, so that one's wrong. And the last one here, the NO2 is greater. So we've eliminated B and C already. Now, how does the H plus concentration come in? Well, this is a 0.1 molar HNO2. So let's say we got to the 3.4. Then, half of our acid would have been neutralized. So it might be something on the order of 0.05 molar, and this might be 0.05 molar, something on that order. And if the pH is 5, then we know that the H plus concentration is 1 times 10 to the negative 5. And that's definitely small. So we know that these two numbers are going to be greater than the H plus. So we can eliminate A, and we know that D must be our answer. Okay, and the last question, which of the following mixtures would produce a solution with the greatest buffering capacity? Greatest buffering capacity. Well, let's take each situation. Here's a weak acid, and we're putting in its conjugate base, so that would be a buffer. But we have twice as much of our acid that we have as our base, so that might knock down our buffering capacity because of the fact that it would not be all that good as far as the weak base is concerned. Okay, here with the second one we have HNO2 and NaOH. Okay, well that is going to form a nice buffer. Okay, we're going to have 0.05 moles of acid left over, and we'll make 0.05 moles of our conjugate base through this neutralization, so that's reasonable. For C, 0.1 mole of our acid and 0.1 mole of our NaNO2 base. Okay, so this one is good because it's got the same it's going to have the same chemicals as these other guys, but it's going to have more of them. And here's 0.1 molar acid and 0.1 molar base. Okay, well that's not going to be good because that's going to change all of our acid into its conjugate base, and so it won't be very good. We won't have much acid left in it. So the best buffer, one with the best buffering capacity, because it has the largest amount of our acid and our conjugate base, is answer C. And that's the multiple choice portion of the practice test.